Hi everyone, welcome down to the Building Performance Hub. Today we're going to be talking you through how to do the perfect air tightness test in accordance with the new ATMA Technical Standard L1 September 2021 edition. In order to carry out a blower door test, you're going to need a few pieces of equipment. First, obviously, is the fan itself. This is a Retrotec 5000 series, but there's plenty of models on the market. Some really great fans out there at the moment. You're going to need your fan fabric. You're going to need a manometer, and this measures building pressure both inside and out, as well as the fan pressure, which we convert into flow. You're going to need a calibrated thermometer, and you're going to need a calibrated barometer. A copy of the test standards is always helpful, as well as some approved software. You've got some other parts like your tubes and your control cables. That makes up a full set of blower door kit. So let's get this installed and we'll talk you through how to do a test. So now we're going to install the door template, and we do this like so. The template works by expanding this metal frame with rubber sides into the edge of the doorway. And we do this by opening, pulling, tightening, and using the cam to expand so that we have no gaps around the door plate. Top tip, you are able to seal the doorway if the door doesn't fit. So there are many doors where you won't be able to install the template nice and easily, so you are allowed in the standards to seal around the door. It's really important when placing your tube outside that you do so at least 2 meters away from the fan and away from the turbulent air. So we typically go to the side 90 degrees and put it down. It's also really important when setting out the fan, if you are in an apartment block, you need to make sure that this tube has access to free flowing air. So make sure that if you are in an apartment block with fire doors that might close the air, that they're pinned open. We install the fan with the covers on. It's super important that the cover's on for the next step because we want to measure how the building performs with no airflow through it. So cover stays on for now. Next, we need to set up the tubes, and it's really important that these tubes are set up exactly as the manufacturer wanted them. Or, top tip, in the ATMA application, you'll find the tube configurator, which will show you exactly how the tubes need to be set up in order to get the correct result. So here we have the inside, outside and fan tube shown, and I'll connect them up. Top tip, keep your tubes nice and tidy. You don't want anyone else tripping over them. When setting out the interior tube, it's really important that it goes into the geometric center of the building. So if you're in a 2-story building, such as a house, you should ideally go to the top of the stairs. If you're in an apartment, go into the middle. But remember, you want to be away from the airflow of the fan. So don't put it in the hallway. Maybe just tuck it around the corner of one of the doors. So next we connect our control cable from our manometer to our fan. Next up, it's setting up the software. You need to make sure you're using approved software if you're conducting a test in accordance with the ATMA standards. This is the ATMA iPad app. It's also available on Android. It's super simple to do testing, and all we need to do is synchronize our test, and that will download the data from our lodgement system so that your test is ready to run. You can also set up a test simply by pushing New Test and manually adding the details. But if you're testing lots of buildings on one site, it's much easier to pre-add the information and synchronize the test on site. So we add the footprint, which is 70 meters squared, 70.0 exactly. We add the envelope area, which is 220.57. The volume is 230.9. We add the height, which is important. It's the average height. So the average height of this building is just over 3 meters, 3.1 meters. And it's technically a 1.5 story. So in the UK, we say 0.5 of a story for a warm roof construction. We click to say that we've confirmed our measurements, and that means we've taken real site readings to validate our off-site SketchUps or our off-site drawings to make sure that the plot is exactly as we thought it should be. So we can take a shot of the outside of the building. And that's saved within the test file. So next we add our envelope area evidence. Either you can search for evidence that's already on your iPad or in a file saved on your iPad by clicking the Browse button, or you can simply take a photograph if you've already manually calculated on site. We record the building use, the test type, the area that we test, the heating, ventilation, air conditioning of the building so that we can gather the information as required. It allows us to analyse lots of important information behind the scenes, to look at the industry, and it allows us to compare countries versus other countries as well. So fill in the information. So we record all of the temporary sealing that we do in accordance with the standards. So using method B, which is generally used in the UK, we seal up any ventilation because we're testing the building fabric, not because we're testing the building in use. And it's important to understand that that's very different. In other countries, they'll test a method A, which is building in use. But generally in the UK, method B is the way we do it. So we record that we've tested in this building. The tester has sealed 5 MVHR vents, and we click add. And if we choose to, we can add a photograph of that, but typically we wouldn't do that for any preparation. Next, we add any deviations that might have occurred. So that's things that perhaps aren't finished, and they'll go into the ATMA deviations assessment. So they're assessed by a member of the technical committee who will look at a deviation and check whether or not a deviation is valid. It's important to understand that deviations do occur. This is the construction industry, so do note them. So in this case, we'll say that site used foam in the hallway on some boxing because it was missing its seal. And we add that. And ideally, we take a photograph of that deviation, which gets saved against the job. Next, we seal the ventilation. It's really important. There's 2 things you need to remember. One, if it's a system 3 or system 4, you need to really turn off the ventilation system before you seal it, because you may cause the motor to burn out, and no one wants a brand new home with a busted ventilation system. And number 2, if there's adjustable dampers on the ventilation, don't adjust them, or don't close them instead of sealing them, because chances are it's being commissioned already and you'll ruin someone else's hard work. We need to open all of the internal doors to make sure that the airflow can travel around the building and get to all of the external walls. We need to make sure that all heating systems are turned off because we don't want the air temperature changing during the test. To save time, we take the external temperature right before we set up for the zero flow pressures. Once the temperature is stabilised, we bring it back in, note the temperature, ready to put into our software. We can then close all of the external doors. We take the internal temperature the same way. Remember though, it might take a few minutes for it to settle, so don't take the temperature too soon. Once it has settled, put the information into the app. Next, we take the barometric pressure and put that information into the app. Then, we're ready to get to the fun part. So next up, we take our zero flow, often called fan off pressures. It's important to know that all buildings have a natural airflow through them because air moves from the ground up, heat rises. So typically, air will come in through gaps and cracks low down, will rise up and escape through gaps and cracks high up. Therefore, you have a natural flow through the home. So we need to measure that to make sure that we take that away when we do our test. We do this by taking a reading approximately every 5 seconds and we add it into our app here. We take 10 readings, typically over a minimum of 30 seconds. And that's important so that we can really see what the profile looks like. On a windy day, you may get really high zero flow pressures. Anything above 5 typically means the test isn't valid because the uncertainty levels rise way too high, so you can't be sure of the result. So below 5 is completely acceptable. In this instance, because we're within a building, the zero flow pressures are around 0 to 0.1, which is tiny. I'll go ahead and I'll take the readings and I'll pop them into the app. Before we start the actual test and before we turn the fan on, remember we need to take some of our plugs out. Now, if you're a good air tester or an experienced air tester, you'll know just how many plugs to take away. You make an estimation of the leakage of the building you're in, and sometimes you get it absolutely perfect. Sometimes we'll need to add a plug or take some extra plugs away if we need to change the amount of flow coming through the fan. Today, we're going to start with a C4. C4 simply means on the C-ring, we have 4 holes. So next, we need to take the cover off. So now we're ready to power up the fan. What we normally do is power up the fan quite low, somewhere around about 10 pascals building pressure, just in case something goes wrong or we're not quite sure. It's always best just to start low and work your way up. So I'll set the fan to 10 pascals just to do a quick check of the building. What you can see here, we have pressure A, which is showing minus 10.3, minus 10.4, and pressure B, which is showing minus 6.9, 6.8 there. As a rule of thumb, we want the fan pressure, which is pressure B, to be double what we have on pressure A. That just is a rough rule of thumb to make sure we've got the right flow rate, and it helps us later on. I'll explain later. So because the pressure isn't quite double, as shown, we're just going to block up a couple more of the rings. So what this will do is increase the pressure of the fan. We'll ramp it up and check. You can hear the fan now running up as it works a little bit harder in order to achieve the same flow rate. So the way we test is that we take the building up normally to around about 60 pascals pressure. And what we mean by that is that the inside pressure is 60 pascals different to the outside pressure. Now don't worry, that's not really high pressure, it's not going to damage anything. It's the equivalent of blowing on the back of your hand. It's a very, very small amount of pressure, but it's enough for us to take our readings. What we do is take the fan up to 60 pascals and then we typically take measurements coming down around 10 pascals at a time. Some testers like to go up, but that's personal preference. Once those pressures are taken, they're plotted on a graph, and from that we calculate the leakage rate of the building. So what I'm going to do is run through the test very quickly. We're going to speed this up and away we go. I like to take my pressure readings around 4 pascals apart, and that's because there is a limit that you have to get between 10 pascals of each reading. But if you need to exclude a reading, perhaps because there was a large gust of wind, if you take 4 pascal readings or 4 pascal between pressures, you're able to remove a reading and still be compliant with the test. It's important that we hit at least 50 pascals pressure difference. The standard we report to is at 50 pascals, so we need to make sure on our graph we go through 50 pascals. It's also important to remember that includes the zero flow values. So if you have -5 as a zero flow and you achieve 50 pascals here, you've actually only got 45 pascals, and therefore you've not gone high enough and your test is invalid. So normally try and go at least 55 or over for your maximum reading. Ideally 60, 65 if you can. It's also really important when you get to the lower end not to go below the calibrated range of your fan. And you can look that up on your calibration certificate. Otherwise the uncertainty values are way too high. To comply with the standard, you need to measure at least 7 readings, 7 separate readings. Typically we try and do 10, and that's so we get a much better data set, especially if one of those points is just slightly off the curve. You won't necessarily know if there's a large gust of wind, but it could just throw one of those readings out. If it's really windy, take 15 or 20. Take as many as you can, because ultimately more data is better. You can always remove a reading, but you can't add one back in. Another top tip, if you know your zero flow values might be a little bit high because it's a bit windy or you're testing a particularly tall building, try not to take readings below 25 pascals, because the rule is 5 times the static pressure makes for an invalid reading. So by starting at 25 and going higher, you get a much more accurate test and you won't have to delete readings. And that's it. On this occasion, we've got 9 readings. They look good to me, they look sensible. So we're going to turn the fan off and the whole process gets reversed. So we cover the fan up. After around a minute or so, we'll take our zero flow pressures, we'll retake our barometric pressure, and we'll do internal temperature and external temperature. That should give us a result. We have our final test. As you can see exactly how the test is calculated, we plot the points on a logarithmic graph, we draw a line, and we're able to then work out the flow. And that flow is divided by the size of the building, so that bigger buildings tend to perform that little bit better because they have less leakage per unit area. What you can also see here is that the airflow exponent is 0.581. That needs to be between 0.5 and 1 to be a valid test, so that's great. The lower the airflow exponent typically means bigger holes in the building. If that's normally at 0.8, 0.9, it means there's very few small holes in the building. The coefficient of determination, R², that's an accuracy measure of how accurate the data is in a straight line. So that needs to be 0.98 or above, or generally it's 98% is what we would say. So this test here, 99.8% in terms of its accuracy. So we've got a final air leakage of 838 meters cubed of air per hour, and we divide that by the size of the building to get a final result there of 3.53, and that's the full test. What we're going to do now is do some diagnosis. So we'll chuck some smoke around, we'll see why this building isn't achieving less than 3.53. We do that using a variety of methods. So we have smoke pencils, we can use smoke guns. Generally, we use the back of our hand. So we're able to walk around the building and feel where the cold air is coming in. In hot countries, it's warm air. And that gives us a clue. Most testers will do that on almost every test, just by habit. In order to best utilize smoke when we're looking for leakage areas, we need to pressurize the building. The test we did was a depressurize, so we were drawing the air away. Now we're going to push the air in to create a positive pressure difference. And what will happen is when we use our smoke pen, the air will escape, or the smoke will escape through the gaps and cracks. And that will allow us to see exactly where the building's leaking. It's not always the best way of looking for dwellings, because sometimes smoke can go down a path and through another path up a little bit before it makes its way out of the building. But it's a great way of seeing where that exit point is and trying to figure out exactly where that leakage might be. So let's spin the fan round. We're going to use a smoke pen. We're going to create a small amount of smoke, and we're just going to see where that smoke disappears, see where we can improve. What we're going to do is open the fan up really wide. So rather than have it restricted and controlled, we're just going to pop this ring off. It's important you create a lot higher pressure than you normally would for a test when you're searching for leakages. It just makes them more obvious. But what we have to be careful of is not over pressurizing the building, because a building like this that uses membranes, a quick burst of air could rip or break the membranes. So we don't want to do that. So we'll still take the fan up gently, exactly as before, but we'll just increase the pressure by increasing the flow through the fan. So here you can see the smoke being pulled out through a gap in the membrane. And this is typically where a trade has accidentally punctured the membrane during construction. But the amount of air being pulled out is quite significant. As you can see here, there's a small leak coming under the window sill, just drawing air through under here. So this area needs sealed. There's something definitely gone wrong behind the plasterboard. So thanks for watching. That's how to do a perfect air tightness test in accordance with the new ATMA standards. Make sure you download the new ATMA app. Both the standards and the app are completely free. And join us next time as we do more videos and produce more content for you. Thank you very much.